X and Y intercepts, and again, if this is super easy and elementary for you, just bear with me. We will get to the beef. Trust me, the calculus is difficult once we get to it. It's just the intro is not bad. All right, so intercepts are where points where a graph intersects the x or y axis. An x-intercept occurs where y equals 0. A y-intercept occurs where x equals 0. A function can have 0 x-intercepts or multiple x-intercepts, but it can only have at most one y-intercept. It doesn't have to have any y-intercepts, but it cannot have more than one y-intercept. So x-intercepts on this line right here is where your y is 0. Your y-intercepts is where your x is 0. So just visually, that's what you're looking at there. All right, so examples. We'll do maybe, I don't know, maybe 2 of these, maybe 3. All right, so this first one, your x-intercepts are where your graph crosses your x-axis. So what does it look like? 1, 2, 3, maybe 4 right there. So your x-intercept would be 4, 0. Y-intercept is where it crosses the y-axis, which is at 2 right here. So 0, 2. Let's do 4 and 6. So x-intercepts on number 4 here. So we actually don't have any, right? So we have no, it doesn't cross the the x-axis anywhere. So our x-intercepts, we don't have any. And then our y-intercept is where it crosses the y-axis. 1, 2, 3, 4, 5. Looks like right there, 5. So 0, 5. You can have multiple x-intercepts. So this is an example of that where we have one here at 1, 2, 3, 0, 4, 5, 6, 7, 0. So you got both of those. And then y-intercepts, we have one down here at negative 1, 2, 3, 4, 5, 6, 0, -6. All right, so just a quick reminder about x and y intercepts. For function analysis, those become more important later. Okay, so zeros, another word for zeros are x-intercepts. Or sometimes you'll refer to, you hear them called the solutions to the equation. And then to find the zeros in the y-intercept algebraically, to find the zeros, you set your y equal to 0 and solve for x. And then to find the y-intercept is where you find where x equals 0. So we're looking for f of 0 equals what in function notation there. We hit on a lot in calculus, especially in that first in unit 1. So, but some of this is stuff that you've learned in advanced algebra, algebra 2, so earlier in your math career. So continuity basically is where the graph is continuous. So a graph is said to be continuous. Oh, there we go. Continuous if there are no poles or asymptotes in the graph. If there are breaks or holes in the graph, it is considered to be discontinuous. So basically, if you can start on the left with your pencil and move all the way to the right without ever picking up your pencil, it is continuous. And if that is not possible, it has discontinuities and thus is discontinuous. So first of all, we have several different types of discontinuity. So we have infinite discontinuities. So an infinite discontinuity is when the function increases or decreases infinitely, hence the name, as x approaches some x value from the left or from the right. So these are also known as asymptotes. So an infinite discontinuity just means it's an asymptote. So we have an asymptote right here at x equals a. So your asymptote is where your function approaches the value but never crosses it. So it approaches a but never crosses it, at least in that general vicinity. So we also have jump discontinuities. So a jump discontinuity is basically where you can follow the graph along, but then you have to jump to get to the next location. So I can hold my pencil here, but then I'm gonna have to jump up here to pick up the function back up. So jump discontinuity, just where it jumps from one point to another. Important to note here that this is only a function if these are not both filled in, right? So if this is filled in, that means the function value exists here, but does not exist here. Both of these were like complete filled in circles, then it would not technically be a function. All right, and then our last type of discontinuity is called a removable. And these are always just holes. So removable discontinuity basically just means I could put something into that spot very easily, just one single point, and make it continuous, but it is not continuous right now. So as I trace this function along, everything's good. I hit a hole right here. This is a removable discontinuity, and then I can pick it back up. But if I filled in that single point, it would be continuous and everything would be great. So it's continuous everywhere except for the hole at whatever value you have. All right, so I want to give you maybe like 3 minutes to look at these 6 graphs, and maybe only 2 minutes, it shouldn't take long. Determine if it is continuous, and if it is not, identify the type and location of discontinuity. So take about 2 minutes and do 1 through 6. I would love to hear somebody's voice. If anybody would feel comfortable, would somebody unmute and tell me what you got for number 1? Is it continuous or not? And if not, what type of discontinuity?
For the first one, I said it wasn't continuous, and I think it's a jump discontinuity.
Yes, perfect. Something to clarify, so this paper doesn't really get into it, but these are also called non-removable. So sometimes you'll see it written as a non-removable infinite discontinuity or a non-removable jump discontinuity, and then these are referred to as just removable. Okay, so perfect. So jump discontinuity at x equals, what is that, -1, 2, 3, 4, 1, 2, 3, 4, 5, -5. These boxes are really tiny. All right, what about number 2?
It is a continuous function.
Yes, it is a continuous function. You can trace it all the way from left to right, no problems. What about number 3?
It's discontinuous and it's infinite.
Yes, perfect. So infinite discontinuity at x equals, look like 1, yeah. All right, I'm gonna give you 4 because that's an easy one. 4 is continuous as well. No holes, no jumps, no breaks, no asymptotes. What about 5?
It is discontinuous and it's like a jump function.
So this one, it is discontinuous. You are correct. So discontinuous.
Oh, sorry. I meant sorry, removable.
Yes, perfect. Good check, good catch. So removable, because there is a hole at, what is that? X equals -3. All right, and then 6, we actually have a couple things going on here. It's actually really hard to see. Let me zoom in a little bit. So one thing I know it's discontinuous for sure. Not how you spell that. So discontinuous. I got a removable at x equals 1, 2, 3, 4. And then this one is kind of hard to see here, but it looks like I've got, because of this arrow right here and this arrow right here, there is a line here, which is kind of weird. This is giving me a little bit of a pause. But because I know that arrow is going down, I'm going to say that there is a infinite discontinuity at x equals 2 as well. So even though there is I guess technically a function here of x equals 2 in that vertical line, it's hard to tell, but this arrow is approaching this line, and this arrow is approaching this line, but it's never actually going to meet that. So I do have a discontinuity there as well. All right, perfect. So we're gonna hit a little bit into slope. So I'm just gonna do 1 on this first section, and then I'll do the others too. Because we hit a lot more into average rate of change than we do slope, even though they're the same thing. So, all right, so if you remember slope way back from like middle school, very early math stages, we have slope as being rise over run, right? So our rise here is 1, 2, 3. So I'm rising 3 and then running 1, 2, 3, 4. So rise 3, run 4. So my slope here would be a positive 3/4. If you needed to find the slope between 2 points, you could use the slope formula. So our slope formula, and we do actually use this formula a fair amount in calculus because they ask us about average rate of change a good bit. So our slope formula, y2 minus y1 over x2 minus x1. So we have 2 points here, and it doesn't matter which 2 you choose, right? So, or not which 2, but which point you start with. But you do need to be consistent. So typically you're going to start with your second point. So in this case, I would say my second y value is -7. So y2 minus the first y, minus 3, over x2 minus x1, right? So from there, I have -7 minus 3 is -10. And then -5 minus a negative means plus, right? So -5 plus 9 is 4. And then we could reduce that to -5 over 2. All right, so you don't usually see it in that context, typically in calculus, especially, and so you've learned this in other math classes, but you talk about it more in terms of average rate of change. So a lot of the crux, I guess, of calculus is based on the fact that, or I guess the question per se, can change occur at an instant? So a lot of times we talk about change at an instantaneous moment in time. And to do that, sometimes we need to estimate, well, maybe I don't know how it changes at an instantaneous moment of time, but I can take a change between 2 time periods. So that's what average rate of change is. So it's the slope between those 2 points. So, all right, I'm just gonna, FYI, these notes I did not make, so I have no idea what these lines are supposed to be. Average rate of change, this is called I think it might be a unit rate. Honestly, I don't know. We're gonna go with that. Because if you reduce it down, it does become a unit rate. It's the only thing I can think of that would be 2 words for that. So anyway, the formula for average rate of change, this is how you'll typically see it written in calculus. So we use function notation, right? So f of b minus f of a over b minus a. So f of b just means the y value where the x value is b. F of a means the y value where the x value is a, and then b minus a. All right, so we're going to use these examples. So given the function graph below, find the average rate of change on each interval. So the directions are very important here because this can look like an ordered pair, right? But that's actually an interval of x values. So this is x equals -2 to x equals 1. So we first need to figure out, okay, what is f of -2 and what is f of 1? All right, so if I use this function over here on this graph, f of -2 means the y value when x is -2. So x is -2 here, and then your output is that point right there at 1. So I have -2, 1. Purely coincidence that it's the same value as right there. That's just ironic. All right, and then f of 1, I have x equals 1 is right there, so it looks like it's down here. So what is that? 1, 2, 3, 4, 5, 6, 7, 8. -8. All right. And then now we can do our slope formula, right? So f of b is our second point. So that's going to be -8 minus the first y value of 1 over, what are my x values? 1 minus -2. So you have -9 over 3, which is -3. And if you look at the graph, that matches what we would expect, right? Because if I think about average rate of change, it's the slope between 2 points. So it's the slope from that first point to the second point. It looks like it's going down 3 over 1, roughly. So our average rate of change there is a negative slope of -3. All right, take about 2 minutes and do a number 8. 8. I have f of 4, which is 1. So my input is 4, and when x is 4, it looks like the graph is at 1. And then my output, or my next one is f of 0. So f of 0 is on your x-axis. I'm sorry, so when x is 0 is on your y-axis, so which is -7, so it's this point right here. And then just normal slope formula, right? So -7 minus 1 is -8. 0 minus 4 is -4, and then -8 divided by -4 is 2. And again, that matches up with what I would expect the slope to be, given that that is a positive line that would connect those 2 points, right? Okay. Piecewise is a huge concept in calculus because it comes up a lot, especially in the early stages when we're talking about continuous and continuous functions, differentiable functions, all of these things. So it's really important that we know what a piecewise function is, how to interpret it, how to use it, and that kind of thing. So also, just if you were curious, my plan for tonight is to take a 10-minute break about halfway through class, right? So we'll start, we start at 6:30. So we'll go at 7:30, we'll take about a 10-minute break. So yeah, but if at any point, if you need to step away and grab some water or use the restroom or anything, just feel free. Don't feel like you have to ask, just go for it. Okay, so piecewise functions. So like I said, we need to be very comfortable with how to interpret them, how to read them, what they tell us, what they mean, and how to use them. So as we're looking at piecewise functions, they are defined on their domain. I'm going to just jump straight into the evaluating and graphing all this stuff. The notes, we're going to get examples right here. So we're first going to start with evaluating piecewise functions. So we need to be comfortable with this concept of, if this is our domain restrictions. So those tell us, what piece are we looking at as we're talking about this. So this first one asks us for f of -5. So we have to figure out what piece is -5 going to be placed in. So to think about, does it make this inequality true? -5 less than -3. Is this true, or is that true? Well, -5 is definitely not greater than 7. It's not between -3 and 7. So because this is true, this is the piece that I'm going to evaluate it in, right? So I can go ahead and just plug that straight in. So I have 2 times the absolute value of -5 minus 5. So -5 minus 5 is -10, but because it has those absolute value bars, that's going to become a +10. And then 10 times 2 is 20. All right, let me get rid of this. So typically we're just going to kind of think through this in our head, right? So f of 2, 2 is my input here. 2 is not less than -3, so that piece is out. 2 is between -3 and 7, right? So 2 is greater than -3, but 2 is less than 7. So because it makes this inequality true, we're going to plug it into this middle piece. So we're going to have -2 squared plus 4 times 2. So when you're evaluating these, it's important to remember to use the order of operations. So we have to square it before we use the negative. So 2 squared is 4, and then we're going to multiply by that -1 in front and make it -4 plus 8. So -4 plus 8 is 4. All right, and the last one, f of 7. So f of 7 is not less than 7, but it is equal to 7. So we're going to use it in this piece on the bottom. So it's going to be the square root of 2 times 7 plus 6. All right, so 2 times 7 is 14. 14 plus 6 is 20. So this is going to be the square root of 20. So the nice part about calculus is you don't ever have to simplify, which I know sounds crazy and sounds like bad math. And frequently I will simplify just because it makes, when we get to more complex problems, it'll make it easier to figure out the final answer or maybe, get the right answer in some capacity, but you don't have to simplify, meaning like if you were to leave something like this, you would get the right answer, even though that could be simplified into, a simpler rational form, or sorry, simpler radical form. So the square root of 20 is the square root of 4 times the square root of 5. So I can make that 2 root 5, but it is important to note that I do not have to. All right, I'm going to give you a couple minutes to do number 2. I do want to pause for just a second and let you know what this means if you have not seen it before. So in transparency, that almost never comes up. Like it is very, very rarely used. So I think, honestly, I'm not even totally sure. I'm pretty confident though that this, so if that tells you anything, this is how rarely this comes up. I think this is for the, what it's called like the nearest integer function. So the nearest integer function basically just means like you take whatever it is and round to the nearest integer. So like if I plugged in 6.9 into this, 6.9 minus 4, I would just take that and round it to the nearest integer, so it would be 3. So that's what this is referring to. So, but take about 2 minutes and do ABC on number 2. All right, let's talk about number 2, part A. All right, so G of -3. Somebody unmute, tell me what you got.
Negative 6.5 for this.
Okay, so let's think about where.
Nope, I realized -3 is not less than -4.
You were so correct. So -3 is not less than -4. So I know this one threw me off too because I was expecting it to go in order and then they did not go in order. So -3 is not less than -4, so I can't put it there. So if I look at this next one, -3 is between -4 and -2. So that is in fact correct. So this one is going to be 8. This middle one, B, I have G of -8. So if I think about what piece I need to plug that into, -8 is in fact less than -4. So I'm going to plug it in here. I got 1/2 times -8 cubed plus 7. So this is where I was mentioning a few minutes ago where you don't have to simplify in calculus. You don't. So technically, you could leave the answer just like that and you would never have to do anything else. And that's a mathematically equivalent answer to what the actual like final simplified answer is. So you could leave it. It does make it more difficult sometimes to figure out the right answer if you don't simplify. But just important to note. So if you were having a mind blank and couldn't think about what -8 cubed is, you wouldn't necessarily have to do it, right? So because another thing to note, calculus is a very much not calculator friendly class. So you very rarely have a calculator. There are a couple of units where you'll use it, but very rarely. So 8 cubed might not be something you know off the top of your head, but anyway, so 8 times 8 times 8 is 512. Because it is a -8 and I'm cubing it, I have 3 negatives, so it's going to stay negative. So I have -512, and then half of 512 is 256. So I have a -250, -256 plus 7. So what is that? 249. Yeah. Yeah. All right, 3.1. So G of 3.1 for part C. 3.1 is greater than -2, so I'm in this piece down here. So it is this weird notation thing. So I have 3.1 minus 4. There's really two different ways you can think of this. You can think of this as 3.1 minus 4 first, which is -0.9. Or you can think of it in terms of, well, I know I'm going to end up rounding this to the nearest integer because that's what this little notation means. So if it's the nearest integer function, let me just go ahead and round this to the nearest integer. And then 3 minus 4 is -1. So kind of either way you think about it, you're going to get the same answer. But basically, those bars just mean you're rounding to the nearest integer. That is very, very rarely seen. Like I've never seen it on anything in College Board or AP Classroom or anything like that. So it is rare. All right, we will do this last problem and then we'll go and take our break just to end on a nice spot. So, all right, graphing piecewise functions. You won't ever have to graph a piecewise function in calculus, but it's helpful to understand how the graph would look for certain things that we do. So even if you wouldn't necessarily have to graph it out by hand, it is something that you might want to visualize. So there is value in that. So, all right, first thing we're going to do is I like to think about my I call it the connection point first, right? So this is where things are going to happen. So before 0, to the left side of 0, I have this absolute value function. And then to the right side of 0, because this is greater than, right? To the right side of 0, I have 2x minus 5. So I personally think a linear function is easier, so I'm going to start with that one. So to the right side of 0, I'm going to think about this function. I'm going to start by plugging in 0 into this. So 2 times 0 is 0. 0 minus 5 is -5. So 1, 2, 3, 4, 5. So I have 0, -5. And that's going to be actually on my graph, right? Because this is, let me erase that so you can see. This has the equal to sign right here. So that means this section of the graph is actually on the 0, and then this one is not going to touch 0. And then there's two ways you can do this. You can continue to plug in values here to the right of 0. So like 1, 2, 3. Or you can remember that this is just a linear function. -5 is the y-intercept. So 2 is the slope. So I can go up 2 over 1 and continue moving to the right. And then like so. All right, for the other side of the graph, I'm still going to plug in 0, and then because this is a it is not equal to, I'm going to have a hole there, so it's going to be an open circle, but I'm still going to plug it in, right? So 0 plus 3 is 3. The absolute value of 3 is 3. 3 minus 1 is 2. So I have the point 0, 2, and it's going to be an open circle. All right, and then I need to plug in values to the left of that. So, and we can kind of cheat on this too and remember what this is going to look like. So if I think about what this function is going to look like, this is an absolute value function. Absolute value functions look like a V, and they have a vertex similar to a quadratic in that it's the opposite of this. So -3. And then the y value is on the end, so -3, -1. So -3, 1, 2, 3, -1. So my vertex is going to be right there. And then because there is no coefficient in front of the absolute value, it just has a it's not really a slope, but it's kind of a slope of 1. So we're just going to go up to here. And then I have the same thing on this side. Oh. That's going to go out here. All right. It's important to note that you could have plugged in values, right? So if I had plugged in, let's say like a -2, I plug in a -2 right here. -2 plus 3 is -1. absolute value of -1 is 1. 1 minus 1 is 0. So that matches up here. So if you did not recognize or didn't remember that this is how absolute value graphs look, or perhaps you were only on one side of it and you didn't have the vertex or any number of things, you could make a table of values and get this as well. Okay, so our domain. So for our domain, we're going to look at our x values, right? So x values, we are going to say, so it starts over here. This is goes forever in this direction. So I'm going to say it goes from -infinity. And then different people will do this different ways. So I'm going to show you both ways. I think technically the most correct way to show that, like, hey, there's something weird going on at 0 here is to say this first one's going to end at 0 with an open circle. And then the next one is going to pick up at 0 and then go forever in that direction. Technically, because this has a bracket right here, we're not excluding 0. Technically, you could just think of this as -infinity to infinity. These mean the same thing, but and I would imagine that different textbooks would argue this different ways, but I kind of like this better because this shows me this isn't really just a continuous function, right? Because this would be the domain of a continuous function. This is actually not continuous. So I've got something weird happening here at 0, and this gives me that information that just saying -infinity to infinity does not. Even though this one is inclusive right here, so it does have a function value at 0. All right, and then range. So range, I'm looking at my lowest y value to my highest y value, right? So my lowest y value is down here. It never goes below this value. So -1, 2, 3, 4, 5. And that is inclusive at -5. And then it goes up forever. So even if I just disregard this function altogether, this goes up forever from -5 to infinity. And that encompasses all of these values over here as well, right? So everything that's in this red section is going to be encompassed in this blue as well. So I can just go from -5 to infinity. All right, and then discontinuities. So this is what we talked about a little bit earlier. So discontinuities, this is not a continuous function. So there is a big issue here at 0, right? So we said this gives us that information that, hey, there's something going on at 0. So this one is called a non-removable, and then it's a jump discontinuity because it jumps from right here to right here. So there's that gap in the middle. So non-removable jump discontinuity at x equals 0. So we're gonna do 2 examples on this page, and then we're gonna jump to a different set of notes. So for this page here, we're gonna do number 4 and then 6. So 5 we're gonna get to in a second. Not that specific problem, but a type of problem like those. So we're just gonna do 4 and 6, and I'm actually gonna have you do it. So it works the same way as what we just did here on number 3. So take a few minutes. This one's gonna take a little bit longer just from the graphing standpoint. So for 4 and 6, graph them first, then identify their domain, range, and discontinuities. So I'm going to give you maybe 6 minutes to work on graphing those and answering the questions. All right, let's talk about number 4 first. So again, I always worry about the connection point first. So I'm going to worry about -3. I'm going to start by plugging that into my first function here. So I have -4 minus a -3. It's going to turn into -4 plus 3, right? So -4 plus 3 is -1. So -3, 1, 2, 3, -1. So I know I have that point on that left side. And then I know my slope here is going to be -1, right? It's my coefficient in front of my x. So I have a -1 slope, but it's not any further to the right than -3, right? So this means x is less than -3. So I'm going to go back this way. and then keep on going. And because this has the equal to bar under here, this is going to be a filled in circle for that first function. Okay, and then I have x is greater than -3, so I'm going to plug in -3 into this one. So I have -1/2 -3 squared. So -3 squared is 9. 9 times -1/2 is -9/2, which is -4.5. So -3, -1, 2, 3, 1, 2, 3, 4.5. No, but it's going to be an open circle right there. And then I'm just going to plug in numbers nearby that, right? So I can kind of, again, think about what is this going to look like. So this is a quadratic function. It is really helpful to know like your parent functions and what they look like. It's a quadratic function. The vertex is just 0, 0, right? The only transformation that's happened is it's been vertically stretched. So I know if I plugged in a 0, I would get out a 0. If I plugged in, let's say like, let's go -2. If I plug in a -2 here, -2 squared is 4. 4 times -1/2 is -2. So I know I'm going to have this piece here. And then I can use what I know about symmetry of quadratic functions to know that there's also going to be a point over here. And then another one over here. Kind of trying to mirror that one. And then I know quadratic functions make this parabola shape. Okay, so it's going to look something like this. My domain here, again, technically, this does have all real numbers as possible values for your domain. I'm going to be a little more specific, though, and say this goes from -infinity to, what is that, -3, sorry. I'm going to put the bracket on this side because I know that's where the -3 is included. And then my domain for the rest of it is from -3, nope, sorry. That should be a parentheses. -3 to infinity. So this just gives me a little bit more information that, you know, there's something weird going on at -3. All right, and then for my range, so this is going down to -infinity. This is going up to -infinity. There is no function value here, but because this is over here, that y value is still met at some point. So I don't have any, there's no way for me to even really break it up to show, you know, there's something weird going on in this graph. So our range here is just going to be -infinity to infinity. And then discontinuities. So for discontinuities here, this is going to be very similar to the last one. It is definitely discontinuous because there's an issue right here. I can stay, I have to pick my pencil up to get back to the graph. And again, this is called a jump discontinuity. So non-removable jump discontinuity at x equals -3. All right. Like I said, we're gonna do some similar to 5 in just a second. So let's jump down to 6. Okay, so 6, I have several things going on. And this is just a matter of preference, but anytime I see something that's just like a line, and no slope, just a horizontal line, I try to take care of that first because it just makes my graph seem easier in my brain. So I have from -1, or sorry, I have -1 from -4 to 2. So -1, 2, 3, 4. That's going to be an open circle. And then all the way to 2. And that's going to give me my closed circle on this side. All right. And then now I'm worried about 2 different connection points, right? So now I'm thinking about this -4. If I plug in -4 over here, 3 times -4 is -12. -12 plus 8 is -4. So for this side, I'm going to have, what did I just say? -4, -4. So -4, -1, 2, 3, 4. And I know my slope here is 3. So I'm going to go down 3 over 1. And so I know that piece is going to look something like that. And then same idea for this right side. I need to worry about 2. So I'm going to plug in 2 here. So 2 minus 2 is 0. 0 squared is still 0. 0 minus 5 is -5. So I have 2, -5. 1, 2, 3, 4, 5. So I'm down here. And that should be an open circle. And then I can think about my quadratic or just plug in numbers. I know I'm kind of close to the edge. So if I plugged in like, what did I just plug in 2? If I plugged in 3, 3 minus 2 is 1. 1 squared is still 1. 1 minus 5 is -4. So that's going to be, oh, right here, sorry. And then if I plugged in, let's try something over here. So what is that? 2, 3, 4, 5. So maybe if I plugged in like 6. 6 minus 2 is 3. 6 minus 2 is not 3. 6 minus 2 is 4. 6 minus 2 is 4. 4 squared is 16. 16 minus 5 is 11. That's going to be really high. Maybe I should plug in like 4. 1, 2, 3, 4. 5. We'll plug in 5. 5 minus 2 is 3. 3 squared is 9. 9 minus 5 is 4. So 4. 1, 2, 3, 4, 5. 1, 2, 3, 4. All right, just trying to get a general shape. And again, I know I can kind of check this. I know I have a quadratic function, so it's going to be a parabola. Opens up because the number in front is positive. The vertex here is actually 2, -5. So this is the vertex, so I'm only have the right side of this graph. All right, so domain here, I'm going to split this up a couple times. Even though it is a function, all values of x are possible. It's just going to be more helpful to see, what's going on if I split it up. So I'm first going to have -infinity to -4. And it is included on that first piece. Then -4 to 2. This one is included. And then 2 to infinity. All right, and then range values here. So this goes down to -infinity. Coming up, I don't have this y value here, but I do hit it over here, so I don't have to worry about that. I hit, this one here. I don't have anything here, but I do have them over here. So these are all hit. This is hit and everything. These are all hit forever. So this looks like it's just -infinity to infinity. And then this one, I'm going to have 2 discontinuities here. So both of them are jumps. So jump discontinuity at x equals -4, x equals 2. So again, is the skill of actually graphing these important in calculus? No, but is it important to understand how piecewise functions work and what type of discontinuities they can create? Yes, because those questions are asked very frequently in Unit 1. So that is very important. All right, so the next page of this is talking about composition of functions, and then the next one's inverse functions. We're going to come back to that later in the foundations course if we have the time to spare. It is not something I'm super worried about because you don't need it for very many topics. What you need for a lot of topics is understanding rational functions and their key features. So this is this is on Google Classroom in the folder for tonight, and I think it's called key features of rational functions or something like that. So I'm going to give you about 2 minutes to pull that up, and then we're going to go through this because this is going to be very, very important information for Unit 1. So I'll give you about 1 or 2 minutes to switch out your notes. And feel free to do whatever you want to do as far as taking notes for this. I will post them in advance on Google Classroom. If you have an iPad or something and you can just or a tablet or of some sort and you can download it and write on there, that's totally cool. If you want to print it, you can, or if you prefer to just kind of jot your own notes down on your own paper and go from there, I'm good with that too. Like I said, they're your notes, so you can do whatever suits you best. I will post. I'll have to figure out how to do that because I'm not super familiar with Google Classroom, but I will figure out how to post the completed notes that I take in class. That way you can have those as well. So if you miss something or want to compare later, you can do that. All right, so we're gonna spend the last 30 minutes talking about rational functions. So rational function is a see, this is what I didn't write these either, so I don't know. A rational function is a division of, so that doesn't really sound right, but we're gonna go with it. Is a division of two polynomial functions. All right, so we've already talked a little bit about this with holes and asymptotes and discontinuity, but we're now gonna kind of go into them from a standpoint of what do they look like algebraically, and what does that tell me about the graph? So we're gonna first talk about holes. So your first thing that you're almost always gonna want to do on these is factor and simplify. So if you like, this comes up all year, and I tell my students all year, what does it feel like you should do when you see a quadratic? Almost always you're gonna have to factor it, right? So when I see a quadratic, my brain is just already going to, hey, I'm gonna need to factor this. So in the numerator here, I have an x squared and a 3x. So these have a GCF of x. Then I have x minus 3. So I'm dividing out an x here. And then on the bottom, this is a difference of perfect squares, right? So x squared minus 9, I can factor to x minus 3, x plus 3. All right, so you might notice something here. I have the same factor on the numerator and denominator, right? So I've got an x minus 3 on the top and an x minus 3 on the bottom. I can't cancel terms, but I can cancel factors. So I have the same factor on top and bottom. So this is going to simplify down to x over x plus 3. Okay, so anytime that happens, if you have the same factor in the numerator and the denominator, that is going to cause a hole because they cancel out. That makes the hole. So we're going to set that factor equal to 0 and then solve, take the value for x, plug it into your simplified rational, and then solve for y, plot as an open circle. Okay, so we're gonna start with this. All right, so I just said that whatever cancels is your hole, right? So my hole is created by this factor right here. So my factor here is x minus 3. So I need to set that equal to 0. Solve for x first, right? So x equals 3. If I add 3 to both sides, then you're going to plug that back into your simplified rational. So if I plug that back in to what I had left over, I'm going to have 3 divided by 3 plus 3. So 3 plus 3 is 6. So I have 3 over 6, which is 1/2. So my hole here is going to be 3 comma 1/2. So I know on this graph, 1, 2, 3, 1/2, I'm going to have an open circle right there. And there's definitely more going on the graph. We're going to get to that in a second, I believe. Yeah. We're going to combine all of this towards the end and get it all in one graph so we can see how all the different pieces affect the graph. But for right now, we're just going to plot that. Okay. Other things you have to worry about are vertical asymptotes. So again, your first step when dealing with any rational function is factor. All right, so up here I'm looking for factors that multiply to x squared plus 2x minus 8. So you needed to multiply to -8 and add to 2. I'm going to have x, what is that going to be? Plus 4x minus 2. Yeah. So, and then on the bottom, the x plus 3. Okay, so we notice that nothing cancels here. So because nothing cancels, I have no holes. So vertical asymptotes are factors in the denominator that are not this, that are not the, I'm just gonna say not the same as the numerator, meaning they don't cancel. Okay, so we're gonna set the factor equal to 0 and solve. Graph a vertical line, or a vertical dashed line, I already said line, vertical dashed line through that value on the x-axis, and then just note that you can have more than one vertical asymptote. So when I'm looking at this here, I want to know factors in the denominator that are not in the numerator, so meaning they're not going to cancel out. So this factor here that's not going to cancel out is the x plus 3. I'm going to set that equal to 0. Subtract 3 from both sides and solve. So I know I have a vertical asymptote for this function at -3. So 1, 2, 3. And I'm going to have a dashed line. Through there. So, and again, I'll worry about what the rest of this function looks like towards the bottom. I'm just going to get to the main vocabulary right now. But that's going to tell me, so something about this graph, it's either like going up on both sides like this, it could be going down on one side, up on the other, or any combination of those. So you have different options. Okay, so, and frequently as you're looking at these rational functions, they're going to have all of these. So you're going to have a whole, you're going to have vertical asymptotes, you have horizontal asymptotes, you have intercepts. All these things are using are key features of the graph that we can use to figure out what's going on. All right, so horizontal asymptotes. For horizontal asymptotes, we're going to look at the degree of the original rational. So it's important to note that I always do this first because I don't need it simplified. I need the original one. If the degrees are the same, you divide the leading coefficients. And that is your horizontal asymptote. If the degree is bigger on the bottom, your horizontal asymptote is y equals 0. The degree is bigger on the top. There is no horizontal asymptote, which really means it's going towards some kind of infinity. So let me add that in here. It means it's just growing without bounds. So it's going towards either positive or negative infinity. All right, so here's some equations here, and then we're going to match it to which one it would be. So remember, your degree is your highest exponent. So if I look at the degree of the original rational, the degree on the top is the highest degree in the numerator is 2. Highest degree in the denominator is also 2. So they are the same because they have the same degree. I'm going to divide the leading coefficients. So my leading coefficient in the numerator is a 1, and then in the denominator is a 2. So that vertical asymptote is going to be y equals 1/2. So this one is going to be C, because that y equals 1/2 is right there. All right. If I look at the second one, degree in the numerator is a 1. There's no exponent here, so that means it's a 1. Degree in the denominator is a 2. So this is bigger on the bottom. If it's bigger on the bottom, the vertical asymptote is 0. So that is going to be A. And then on the next one, if I look at the degree here, the degree in the numerator is 2, degree in the denominator is 1. It is bigger on the top. So because it's bigger on the top, there is no horizontal asymptote. So this one is B. All right, so x-intercepts we talked about a little bit, but now we're going to talk about them in the nature of rational functions. So a rational function can have 0, 1, or multiple x-intercepts. For fractions, the denominator cannot equal 0. So to find your x-intercept, you set only the numerator equal to 0. Wholes cannot be x-intercepts, so we have to simplify first, and then we only use the numerator. All right, so for this first example, if I set the numerator equal to 0, right, there 1 does not ever equal 0, so there are no x-intercepts. For example 2, I want to simplify first. I have an x plus 2 in the numerator and the denominator, so those are going to cancel. That means it's a whole. That's important information, but I'm only worried about the x-intercepts right now. So once those cancel out, I'm using the whatever is remaining in the numerator, and then setting that equal to 0 and solve. So my other x-intercept is going to be 7, or 7 comma 0. All right, and then example 3, factor if possible. I can't factor this one, right, because 5 is not a perfect square. So can't factor this, so I'm just going to set the numerator equal to 0. So I'm going to have x squared equals 5, or x equals plus or minus square root of 5. So I'm going to have square root of 5 comma 0, and then negative root 5 comma 0. All right, and then y-intercept, we don't use this a ton, but to get your y-intercept, you just plug in 0 for x, and then simplify. You only ever gonna have one y-intercept unless the vertical asymptote is at x equals 0, and then there is no y-intercept, and you can use the simplified or the original. All right. Okay, we're gonna skip this because we already talked about domain and range and discontinuities. So let's jump down here to in behavior, increasing, decreasing, positive, and negative. Okay. So in behavior is very, very important because we use it in really everything we've talked about tonight is all for unit 1. So in calculus. So as we talk about in behavior, we read the graph from left to right, right? So as I look at this, at the in behavior, as x goes to negative infinity, what does y do? So as x goes to negative infinity, y is approaching this asymptote, right? So that's the definition of an asymptote, is a value that something approaches as you go towards infinity. So as I go towards negative infinity, my function approaches the y value of 1. And then as I move towards the right, as I approach positive infinity, that's what that says, as I move to the right, as I approach positive infinity, my function value approaches 1 as well over here. All right, intervals of increasing and decreasing. So increasing just means, generally speaking, the function is going up. It's increasing over time. I have a positive rate of change, positive slope. So this increasing rate, I'm moving up as I go from left to right. This over here, also increasing. It's still going up. It's going up at a different rate, so we can talk about that later. But for intents and purposes right now, it is increasing everywhere. So it's increasing from negative infinity to 1, and then from 1 to infinity. So we're just going to split that up there to show that, at the function value of 1, it doesn't even exist because of the asymptote. All right, decreasing. It is never decreasing, right? Ever going down. All right, positive. So where is the function positive? These are all positive y values. And these are all positive y values. These right here are negative y values. So we're going to start from the left to negative infinity up until 1. These are all positive. And then from 1 to 3, these are negative, but then it picks up at 3, and then 3 to infinity, it goes back positive. Nope, I did not mean to put 0. 3 to infinity. If you are wondering, hey, should I put a bracket on 3 or a parenthesis on 3? Well, it depends. Do you think 0 is a positive number or a negative number? Well, it's really not either, right? So I'm going to put a parenthesis on that because I'm not going to consider 0 a positive number. It is neither positive nor negative. All right, and then negative, the function is negative from 1, so all from here until 3, and I'm going to use parentheses on both of those. 1 because it's an asymptote, and 3 because 0 is neither positive nor negative. All right. So on this one, I'm going to do example 1, and then I'm going to have you guys 2, and we're going to work backwards. So we are going the opposite way on this. So first thing, we're going to look at this graph and see if we can create the function from the given graph. All right. Vertical asymptote. First thing, we're just going to identify all of these values, and then we'll worry about putting them in the equation. Vertical asymptote, right here. We have a vertical asymptote at the vertical line that the function approaches but does not cross at x equals 2. I have one x-intercept at x equals 1 or 1 comma 0. Horizontal asymptote, I have a horizontal asymptote at 1, so y equals 1. So the horizontal asymptote is the horizontal line that the function approaches but doesn't cross. A y-intercept, I have 1 right here. That looks like at be 0.5. And then I have a hole at x equals 3. So I have a hole here at 3. And the y value there looks like it should be 2, but it is actually not because it's a hole. All right. So I'm going to kind of work backwards here. So I'm going to start with the vertical asymptote. So my vertical asymptote is x equals 2. That means the factor that created this vertical asymptote had to have been x minus 2, right? Because I'm looking for what would make this 0. So, or like if I set this equal to 0 and then solved, it would have been x equals x minus 2 to get me a x equals 2. We're going to start with that. So now I've got my vertical asymptote done. X-intercept, those are going to go in the numerator. So again, I'm looking for, if I set this equal to 0, I need it to the value of x to equal 1. So I'm going to go x minus 1. Okay, so horizontal asymptote, it is in fact not 0. So my horizontal asymptote is 1. That means my degrees need to be the same, right? So my degrees need to be the same on the numerator and the denominator. And they need to have a ratio of 1. So if I divide my leading coefficients, it needs to equal 1. There are infinitely many answers you could put here. It really doesn't matter. You can put a 2 and a 2, you can put a 3 and a 3, 5 and a 5, whatever it is, they need to divide to 1. So check your x-intercept by plugging in 0. So I need my x-intercept to be 0.5. So if I plugged in 0 here, this would be -1. If I plugged in 0 here, this would be -2. 1 over -2 is 0.5, so that works. So I don't have to fix anything there. And then put the whole in the numerator and the denominator. So I'm going to say x minus 3, x minus 3.